recognizing what we see. So if we see a dog, it's very easy for us to say that we're looking at a dog. Surprisingly, though, until very recently, computers were actually very bad at this. Even the best computer vision algorithms about 10 years ago, if they saw a dog, they might say dog, but they also might say cat. And this was really the case until about 2011. Computers still made many mistakes. So you might be wondering just what is so hard about that? Isn't that so easy for us? So the challenge is that from a computer's point of view, an image is just pixels, and a pixel is just a bunch of numbers. So in order to recognize a picture of a dog, a computer has to take really just this block of numbers and try to figure out that that block of numbers is a dog. And making it even more challenging, any dog can be seen from many different angles and under many different lighting conditions. And each of those creates a different pattern of pixels. But also, of course, different dogs can look very different from each other. So in order to recognize a dog, a computer has to be able to take these different patterns of pixels, whether from a white dog or from a black dog, and say that they're dogs, but also take what might be a very similar pattern of pixels from a black cat and say that it's a cat. So it's tricky because in terms of the pixels, the cat is more similar to the black dog. Sorry, the black dog is more similar to the cat than it is to the white dog, but the computer still has to be able to say that it's a dog and not a cat. So your brain is actually kind of a savant at this. It's very good at this. And the reason this really challenging task seems so easy is that there's actually about 40% of your brain that's dedicated just to visual processing. And the reason it's so easy is that every moment that you're awake, that part of your brain is kind of chugging away behind the scenes, processing what your eyes are seeing. So how does your brain size up to computers? How much worse are they? So one way to look at that is to, in order to understand that, you need to have some kind of common benchmark and see how the human brain and computers stack up on that. So one way of looking at that is to simply take a lot of different images 10 years ago. So bulldogs, recognizing chihuahuas, and this was really the case until looking at that is to simply take a lot of different images 10 years ago. Violins, so screwdrivers, bulldogs, recognizing chihuahuas, and this was really the case until you show them to either people or to computers and just tell them to name what they see. So now I'm going to show how computers and people kind of compare. So until 10 years ago, even the best computer vision algorithms of the time were still very bad at this. And so what I'm showing here is their rate of making mistakes. So back in 2010, if you showed a computer a picture of a dog, it might say it's a cat about 25% of the time. By contrast, at this same test, people only get it wrong about 5% of the time. Now you might be wondering, why do people make any mistakes at all? The reason is that some of these categories are pretty obscure. Not everybody knows what a Tibetan Mastiff looks like. And this wasn't for lack of trying either. Like, people have been studying this problem in computer vision for a long time. These are really the best computer vision algorithms of the time. And it was even the case that it was almost a cliche that if you're giving your sort of psychology or neuroscience 101 lecture about visual perception, that you'd always say something like, isn't the human brain so amazing? People have been trying for years to get computers to do this very basic thing that your brain does so effortlessly. Things are much the same in 2011, but in the following few years, computers suddenly got much, much better at recognizing objects, to the point that they're, according to this benchmark at least, they're actually even better than humans are at this task by now. So, okay, like, you might be saying, so what? Computers have finally caught up to humans in this very basic thing that's super easy. I'm not impressed by that. Show me something that's more intellectually impressive that I can't do. So for my next example, I want to take a time machine back to 1996. Sounds pretty good right now, doesn't it? And among other things, that was the year of the showdown between the chess champion Garry Kasparov and IBM's chess playing computer Deep Blue. So that was seen as kind of this grand battle of humans versus machines. You might remember that Deep Blue won, but one sort of note of consolation at the time was that even though computers were finally won at chess, there was still a much harder game that people were much better at. So that was the ancient Chinese game of Go. It's over 2,500 years old. I'm not going to go over all the rules, but the basic idea is that there's two players, and they take turns putting either black or white tokens on the board. And the way you score points is by surrounding the other player's tokens with your own. So this is a game that's seen as involving a lot more intuition than chess. It's also much more complicated. So there's 10 to the 360th power possible moves in Go. And just to give you some idea of how ridiculously huge a number that is, if you were to take the number of atoms in the universe and then square that number and then square it again, you'd still really only be up to about 1/10 of the number of possible moves in Go. So this was posed as sort of the ultimate challenge for computers. People thought it'd be a long, long time before they ever caught up to people in it. So some people were saying it might even be 100 years after that computers caught up at this more complicated game of Go. That said, the computers got their chance not 100 years later, but 20 years later. So Google developed a computer called AlphaGo that was specialized for playing Go. And they had it square off against the South Korean Go champion, Lee Sedol. So Lee Sedol himself was very confident. He thought it would be a blowout. So what ended up happening? Actually, AlphaGo won in a 5-game series, 4-1. And it didn't just win. People used all kinds of adjectives to describe the way that AlphaGo played. So they used words like creative, beautiful. They said at one point that it made a divine move that seemed weird at the time, but in hindsight, people realized it was brilliant. And Lee Sedol himself called it an entity that cannot be defeated. And sadly enough, he actually retired from Go a few years ago because he realized that he'd never be able to match up. And then, as if that wasn't bad enough, as if to add insult to injury, Google then made a sort of sequel to AlphaGo called AlphaGo Zero that then proceeded to beat the original version of AlphaGo 100 games to nothing. So this is a big defeat of humans by computers, obviously. But maybe you're thinking something like, okay, computers are really good at these sort of cerebral tasks like playing Go, but they'll never be able to do things like write poetry, right? Like something that, maybe requires more creativity and intuition. Just this year, though, that might have changed. So there was, just a few months ago, there was a new program called GPT-3 that, among many other abilities, has the ability to write seemingly original poetry. So the way it works is you can plug in a few lines of a poem. So here I'm showing the poem, "Shall I Compare Thee to a Summer's Day" by Shakespeare, and it'll spit out its own original continuation of that poem. So it writes, "A winter's day when beams of sun are few and skies are gray with clouds intemperate," and it goes on. And you might not think that this version of the poem is as good as Shakespeare's original version, and I'd actually be inclined to agree with you. But what I want to point out is that it is an original poem. If you take the first line of that poem and then plug it into Google, the only results that come up are the website that I got the poem from. So far I've shown you these 3 examples of recent advances in artificial intelligence. We have this system where you can put in a picture and it'll tell you what that picture is. Another system where you can put in the positions on a Go board and it'll spit out what it thinks is the best move. And this other system where you put in a line of poetry and it'll put out its continuation of that poem. So these might seem like, at first seem like completely different sorts of feats, right? Like, what does recognizing dogs have to do with playing Go, and what does that have to do with writing poetry? But the amazing thing, and sort of the plot twist and main point of this talk, is that if you look under the hood, actually all three of these are examples of the same kind of system, which are called artificial neural networks. And all artificial neural networks are ultimately built out of the same very simple ingredients. So in today's talk, I want to first explain what are these ingredients and how do you put them together to do these amazing things. In the second part, I want to talk about the most recent advances in these systems, bringing you up really to the present day and some stuff including from the last few months. And then in the last part of the talk, I want to talk about what's kind of the future of these systems. What's their potential? Do we have anything to be afraid of them? And what are their limitations? So starting with this first part of the talk, what are the ingredients of these amazing systems I've been talking about? So here's kind of the star of today's show. It's called an artificial neuron. And I put the word neuron in quotes because it's inspired by the actual cells that your brain is made out of, which are called neurons. So these are the units of these systems are very much inspired by actual brains. And I'll explain later where exactly that similarity is. So the main thing to know about a neuron is first, it can have different levels of activation. So if it has 0 activation, it's not doing anything. If it has 10 activation, it's doing more. So this is simply captured by a number. Or it might have some intermediate level of activation, like 5. And where does that activation come from? Well, the activation in any neuron comes from input neurons that are feeding into it. And those neurons themselves have their own activation. And additionally, some of these connections to the input neurons are stronger than others. So the way to think about the strength or weight of these connections, that word weight is really important. I'm going to use it again and again, is that it's kind of like the dial, the volume dial on a radio or a walkie-talkie. So if that volume dial is 0, even if one of these input neurons is shouting its head off, the neuron that it's feeding into won't hear anything. Whereas if it's a stronger weight, that should be a 10, by the way. If it's a really strong weight, even if the input neuron is very quiet, then the neuron it's feeding into will hear that neuron at full blast. So now I bring you to the only math in this entire talk, I promise. So how do you get the actual activation for a neuron? So it's very simple. It's just some 3rd grade arithmetic. So what you do is you go through each of the input neurons, and you take the activation of that input neuron, and you multiply it by the connection weight that connects it to the neuron that you're looking at. So you multiply those together, so 3 times 5, and then you add that to the same thing for the next input neuron, plus 4 times 1, and you add that to the same thing for the 3rd input neuron, 3 times 2. So this is actually one intuitive way of thinking about this. So bringing back the example of radios is if you have 3 radios playing in your room and you want to figure out what's the total amount of noise that you're going to hear, that's going to depend both on how loud is the person speaking on the other side of each radio, and also what's the volume dial on each radio, right? So if you think about that, the neuron is actually doing a very similar kind of calculation. And actually, the real neurons in your brain do something of this nature. They're much more complicated, but this is where the inspiration from real neurons comes from. Okay, I promise that's all the math for the talk. No more math after that. So at this point, you might be thinking that you're kind of the victim of a bait and switch, right? I just told you that these systems could write poetry and play Go and recognize images. But now I just told you that all they're doing is taking numbers and multiplying them and adding them up. So the key insight here is that there's strength in numbers. Even though one of these neurons isn't very powerful on its own, if you take many of these neurons and wire them together, they can do amazing things. So what I didn't tell you is that there's not just a few neurons feeding into one neuron. Each of those input neurons itself has input neurons that are feeding into it and driving its activation. And each neuron isn't just driving one other neuron, but driving several other neurons. And these neurons are kind of organized into layers. So one layer feeds into the next layer, which feeds into the next layer. And oftentimes you have many layers. So remember, connections can be strong or weak. And what I forgot to mention is that I'm symbolizing that by the thickness of the arrows. So the thicker the arrow, the stronger the connection, the higher the volume on that radio dial. And so the way these networks work is that they sort of send up activation layer by layer in a one-way street. So you have your first layer of neurons, which is often called your input layer. They send their activation up to the next layer, which, like I explained earlier, each neuron multiplies and adds up the input from the previous layers based on their connection weights. And that happens for each neuron in the network. And then that gets fed into the next network. And then that gets fed into the next network. And often these networks are massive. So I've shown you kind of a teeny tiny network, but often these networks in practice, can have millions or even billions of neurons. So when you wire up your neurons like this, it's what you call it is an artificial neural network. So these are kind of the stars of today's show. So obviously we don't just want millions of neurons talking to each other. We want these networks to actually do things for us, right? So So to be specific about that, we want to be able to put in something like a line of poetry and have it spit out the next line of poetry, or put in the positions in a Go board and have it put out the next move, or put in a picture and have it put out what that picture is of. So I'm going to talk about all of these examples in due course, but I want to begin with this last example of recognizing pictures because historically it's important and it illustrates a lot of the general ideas. So to explain how networks do this, first remember that images are ultimately just pixels, and pixels are ultimately just arrays of numbers or grids of numbers. So in order to input this grid of numbers into the network, the way it works is each of the neurons in this first layer is responding to a few different pixels in the input image, and they have their own connection weights that are connecting them directly to the image. So those input pixels drive our input into the first layer of neurons. As for the output, remember you want it to output what the network thinks the picture is of. What you do is you designate each neuron in the last layer or output layer with the different categories that you want to recognize. So one output neuron might stand for dog, another might stand for violin, and another might stand for shoe. And the activation in that output neuron reflects how strongly the network believes that the image is of that category. So again, the way it works is these input pixels feed into the first layer, those feed into the next layer, which feed into the next layer, which ultimately, if the network is working correctly, will activate the appropriate, the neuron corresponding to the right category. So, okay, we've set up this network. So enough talking, let's take an actual network for a test drive. So I'm gonna show you a network that has 8 layers and 660,000 neurons. I'm not showing them all of them, obviously. It'd be hard to make in PowerPoint, and 6 million different connections. So let's see how it works. Let's put in an image and see what it says. So I'm showing you a screen capture from just a few lines of code that I took. So I'm just putting in a line of code that inputs an image and then it'll put out what it thinks the image is. So if we put in this dog, what does it think the image is? And we get some weird results. So this network thinks the dog is either an airplane or a garbage truck or an abaya or a lobster or breakwater. So what the heck is going on here? So the issue is that this particular network that I used has just random connection weights. They haven't been wired up to do anything in particular. So if you feed in an image and the pixels are fed into the first layer, which are added up and multiplied and fed into the next layer, and then the next layer, and then the next layer, there's no guarantee that after all those layers of adding and multiplying, that it's going to activate the right unit or the right output neuron. So instead of activating the dog neuron, it might activate the airplane neuron. What we want, and again, the issue is that it's the wrong connection weights. So what we want is a network where the weights are just exactly right, so that if you do the same thing and put in the input image and have that go through the network, it activates the right category output. So again, we want to have it set to the right connection weights. So this process of setting the right connection weights is called training the network. And at first it seems kind of impossible, right? Like I told you, there are 6 million connection weights in this network. How can we possibly dial everyone just right? So you put in a bunch of pixels and then activity percolates through the network and there's all this adding and multiplying, and it just happens to activate the right output neuron at the other end. And then not only that, but we have to be able to put in any picture of any dog and have it activate the dog unit, and also have it be able to recognize any picture of any other category too. So the amazing thing is that we don't have to do that manually. In fact, these neural networks are able to learn how to do that automatically. All you have to do is put in, give it a lot of examples of what you want, and it'll gradually figure out for itself what its connection weights have to be. So how exactly does that work? So when this network starts out, before you've trained it and the connection weights are just random, if you put in a picture of a dog, the network might only be 0.1% sure that the picture is a dog. So what happens then is you go through each connection weight And that connection weight either gets dialed a little bit up or a little bit down. So let's say this connection weight gets dialed a little bit up, which I'm showing by making it thicker. So that causes a bit of a chain reaction. So since that connection weight is stronger, the neuron that the connection is connected to becomes more active, and that means that the neurons that neuron is connected to become more active. And ultimately, there's sort of as a result of this sort of butterfly chain effect, chain reaction, instead of the output neuron being 0.1% sure that it's a dog, it might just be 0.11% sure. So what good is that, obviously? So you then want to go through and do the same thing for all the other weights. And maybe at the end of that process, the network is 0.2% sure that it's a dog. So 2 quick points here before moving on. So you do have, in order for the network to adjust its connection weights towards getting the right answer, you do have to tell it the right answer. So you need to not just give it a picture of a dog, but also literally tell it that this is a dog. So the dog unit should be active. The really sort of magical thing here, and the special sauce that makes these networks work, is that once you do that, it's able to automatically adjust its connection weights to get the right answer. So that might seem sort of miraculous at first, like doesn't have to kind of predict what the, for each weight, predict what the chain reaction effect of changing that weight on the final outcome would be. Like, how does it trace, okay, you changed this weight and that changes the next thing and the next thing and the next thing. So it's not magic. There is some math involved, but surprisingly, it's not anything more advanced than first semester, your standard first semester AP calculus in high school. If you remember the chain rule of taking derivatives, it's really nothing more than that. But for now, the thing to take away is that there's a process that does all of this automatically. So far you put in one image, and the network is a little bit more sure that it's a dog. So the way you make it even better is you put in many more pictures of dogs. So maybe you put in another picture and now it's 0.7% sure, another picture and now it's 1.1% sure, another picture 1.3%, and so on. But then you don't just want it to be able to recognize dogs, you also want it to recognize other things too. So you give it pictures of shoes, of airplanes, and then you want it to be able to recognize many categories. So you also give it golf carts and pillows and drills and vacuums, scuba divers, orangutans, cranes, bullfrogs, macaws, guitars, barbells, cassettes, crabs, stingrays, and hamsters. And I would go on, but there's 1,000 categories, each with 1,000 different images in that category for over 1 million images total. And remember, these aren't just images. You also have to have a label for each image saying what it is. So we train the network with all these images. So cue the training montage sequence, and usually that takes a while, at least a few days. But by the end of it, if we then try our same test and put in the same dog image into the same network, we now see that it gets it right. It correctly categorizes Dogue as a Pembroke Welsh Corgi. And just for good measure, I also fed in a picture of my own dog, Lily. So it correctly recognizes that Lily is a Chihuahua. Interestingly, its second guess is Siamese cat, but if you look at Lily, you can kind of understand the confusion. She does kind of look like that. You might be confused by that third guess it has, paper towel, but actually, if you look really closely at the background there actually are some paper towels in the background. So the network is pretty smart. It's identifying what it sees. So let's go back now to this graph I showed you earlier that shows the rate of computers making mistakes over time. So now we can understand what actually happened over this decade. So in 2010 and 2011, actually the state-of-the-art computer vision algorithms then were not neural networks. They used different techniques. But then in 2012, that's when neural networks really finally came into their own. And in particular, there is a specific neural network called AlexNet, named for its creator, Alex Krzyzewski. So one perk of making your own network is you get to name it. And that's actually the network I just showed you. And so that made a big splash when it arrived. It was one of the first really successful neural networks. It was a big improvement over previous algorithms, as you can see. And then over the successive last decade, there were a lot of sort of networks inspired by AlexNet that got bigger and better, and got better and better at recognizing images. until today, at least by this metric, they're even better than people are at recognizing what they see. So interestingly, this is only really the latest chapter in a very long story. So this idea of wiring up artificial neurons and using them to do tasks is not new. Actually, the idea goes back to 1943. That was back when people were just figuring out how real neurons work. So the idea sort of originated in 1943, and then in 1958, the first two-layer network came out, and people realized that there were some cool things you could do with it. But then in 1969, neural networks kind of hit a roadblock. They realized that these small two-layer networks couldn't do even a lot of very simple things. So I don't know how specific to get, but like even something as simple as saying, I want you to respond to apples or oranges, but not to both apples and oranges. It can't even do that. So that was a roadblock, and it led to what's sometimes called the first AI or neural network winter, where neural networks were sort of this underdog. People thought they couldn't work. That said, in 1980, people realized that if you added more layers, you could get around the previous drawbacks of it. 1980 is also when they invented this algorithm that I've talked about that can automatically adjust the weights. And so that made neural networks a player again. They still weren't the leading AI algorithms. There were still other algorithms that were more dominant. So for example, the computer Deep Blue that I mentioned that won at chess did not use neural networks. But finally, in 2012, neural networks sort of had their moment. And that wasn't because there was some big new innovation or conceptual development. Really, all of the essential building blocks were already in place. But what happened was that people finally realized that bigger was better, and there was finally good enough technology to sort of realize the original vision. And by bigger, I mean not just bigger networks, although that's really important. People realized that having more neurons and more layers made these networks much more powerful, and people finally had the computing to run and to train those networks. But we also had much bigger data. So remember I mentioned that you need over 1 million images to train these neural networks that recognize objects. So before the internet, that was impossible to do. Like, how could you possibly collect all those images, and then somebody has to stick the labels on them and say this is a cat and this is a dog. So for a while that was hopeless. But in 2009, there was a computer scientist at Stanford, Fei Li, who led a team that created an image database called ImageNet that had all these thousands or millions of images needed to train these networks. So that was actually a huge breakthrough. And all of the later advances in computer vision kind of built off of that. So people realized that bigger computers, bigger networks, bigger data was what made these networks work. And this arrival of these bigger, more powerful networks started the era of what's now called deep learning. So a quick word about this phrase, deep learning. It's become sort of the latest sexy marketing catchphrase. Every company wants to say they use deep learning. Like they want to say, oh, we use deep learning in our dating app to help you find your soulmate or whatever. But the word deep learning, actually, strictly speaking, it just refers to neural networks that have a lot of layers, as opposed to what are called shallow networks that have just a few layers. So deep learning makes you think deep understanding, but that actually remains to be seen. And I hope you have your own opinion about that by the end of the talk. So all that said, neural networks have really taken off in the past decade. They're used for all kinds of things now. So Facebook uses them to automatically tag your pictures, or at least they used to. I think they discontinued that feature when people got creeped out by it. But your phone's face recognition system also uses it. So now these neural networks are widely used. So I've told you a lot in this first section of the talk. It's a lot of information. So I want to take all the stuff I want to take you away from this part one and boil it down into what I'm calling the deep learning recipe. So the way that all deep learning works is that you start with a bunch of neurons, and then you build them into a network. And by the way, this is the only like manual stage of the process. You do have to tell it how many neurons you want and which neurons are connected to which other neurons. But after and there's a bit of an art to that. There's like some trial and error involved in figuring out like how many layers do you need, how many neurons do you need. But after you've done that, everything else is automatic. You just give it once you've set up this network, you give it a lot of training data, and then the network automatically adjusts its connection weights based on that training data to get better at the task. So far, I've shown you in detail how this works for networks that recognize images, um, but it can also be used for a wide variety of things. So I told you at the beginning of the talk that this same kind of technology can be used for doing things like playing Go and even writing poetry. And in the second part of the talk, I want to deliver on that promise and show you how that's possible. But first of all, are there any questions so far? And feel
Thanks
free to put them in the chat. And yeah.
Yeah, thanks so much, John Mark. As you were just hinting at, if you do have any questions at this time, feel free to ask them in the Zoom chat or the YouTube chat, and we can relay them. And we do have time for a couple questions before we take a short break. So we'll give everyone a minute to get their questions in. If there are no questions right now, then I'm happy to. Why don't we go ahead and take our short break? Stay tuned for lots more interesting information from John Mark, and we'll start again promptly at 7:10. Does that sound good? Great. Thanks, everyone. So get a snack. Stay tuned. We'll be right back. So how about we go ahead and get started again? I noticed that there are a couple questions in the chat during the break. So game time decision, would we like to answer those quickly before we start the next section?
Yeah, please.
Great. Here, Buse, do you want to read those out for us?
Sure, I can read.
Thanks.
This is from Ludmila. If you want to also ask your own question, I can also unmute you, but I'll attempt it myself. So the question is there a clever way to test the weights of each transition during the learning process? She says, I assume that there'll be several sets, which will result in a correct answer, but this may not work for the next training set.
Yeah, great question. So ultimately the neural network is just a bunch of numbers. So the programmer is able to inspect the weights if they want while it evolves. Was that your question? Feel free to unmute yourself. I just want to make sure I understood it.
I think that's it. It's also in the chat, but if
okay.
I can also unmute.
Thank you very much. Hi. No, that was thank you very much, John. That was always my question actually, because I mean the idea is actually very much clear. You have to find a set of weights, right, to transfer from one neuron to another to get a correct answer in the end. My question, and the learning kind of in principle searches for those answers. What I never understood is how it is made, because if you take the combinatorics, especially like you introduce like deep learning, yes, so you have many sets of that. Not a single computer time will manage to do that. So are there like clever mechanisms? How do we search particular for those weights of transitions?
Yeah, great point. So I think what you're getting at is you have to find one very particular combination of every single weight, right?
Exactly. So how this is done, because this is the interesting and tricky part, right?
Yeah, exactly. So I didn't want to dive too deep into the math, but the idea, if I can think of an intuitive way to explain it, is that you can think of, so if you consider just two weights, so imagine an X and a Y axis, and you're curious, what's the error rate of misclassifying the images with those two weights? And your goal is to minimize that error rate. So apologize, I'm going to lapse into some math jargon. If you imagine a
square or something like,
what's that?
It's like minimum square, like when we compare
you're trying to minimize the least squared error, and you do that by finding the trying to find the global minimum in a big multi-dimensional function.
I see.
By the way, people didn't understand what those words mean.
Got you. Thank you very much. That's very similar what our programs in structural biology use. Thank you very much. Never thought of that. That's actually a simple explanation.
Of course.
Yeah. Thank you too.
Great, thanks for the question. And we had one other question from Joe. He's asking, I noticed there are no feedback loops in your neural network, but the brain would have such feedback loops. Do you think this will be added to artificial neural networks anytime soon?
Yeah, fantastic question. And actually, when I was making that talk, like that's the one thing I wanted to add, but I ended up cutting, is the networks I've shown you so far, and the ones I'll end up showing you, are all feed forward in that the connections only go one way. It's a one-way street. But yes, as you mentioned, your brain is full of feedback connections. And there are some neural network. One other innovation recently in neural networks is that some of them have experimented with adding not just feed-forward connections, but feedback connections, so the later layers can feed back to the earlier ones. And actually, I think one of the earlier versions of Siri on your iPhone used feedback networks like that. So the answer is yes. That's one of the many exciting things that people are experimenting with to try to make these networks work better. So unless there's any more questions, and feel free to jump in, by the way. Okay.
You're good. We can do our second part.
All right. So now I want to talk about move on to the second part, which I call the deep learning explosion. So at the end of the first part, I mentioned this deep learning recipe. So you take a bunch of neurons and you wire them together. Then you pour in a bunch of training data, and the networks automatically figure out how to adjust their weights to do the task. And I made you this promise that this worked not just for images, but all kinds of other things too, like playing Go, like doing poetry. So in this part of the talk, I want to kind of deliver on that promise to you. And it might sound crazy, like how do a bunch of very simple neurons that are just adding up and multiplying do these amazing things? But I like to use the analogy of Legos, right? Like an individual Lego is very simple, but if you have a lot of them and are very creative about putting them together, you can build them up into amazing things. So I want to sort of follow up from the previous example of recognizing images and use that to talk about what I think is one of the most clever and exciting advances in neural networks from the past few years. First, though, I want to show you pictures of these 15 people, and I want you to take a few moments and try to think about what all these people have in common. And feel free to chime into the chat and brainstorm or whatever. I'll give you a few seconds. So the answer is, what all these people have in common is that none of these people actually exist. These are photos of completely non-existent people. And they were drawn not by one, but by two neural networks working together. So how does that work? So first, let me introduce you to our two networks, the two sort of co-stars of this story. So the first network I want to call the apprentice artist. Its entire sort of mission in life is to draw realistic pictures of people. So note that this is a bit different from the networks I've shown you so far. The earlier networks that recognized images had it so that you fed an image into the network, but these networks are kind of the opposite. They put out an image. So its goal is to make realistic faces, but when it just starts out, it doesn't know how to do anything. The weights are completely random, so it just puts out kind of gibberish. So how does it learn how to get good at drawing faces? So the secret is that it has a sort of sparring partner, which I'm going to call the refined recognizer. And this network is very similar to the ones I showed you earlier. It's a prodigy at knowing how to tell apart pictures that are real faces from things that aren't faces. So if you put in a real face, it'll say face. If you put in something that's not a face, it'll say not a face. And the clever thing is that you make this apprentice artist better by having it play a bunch of games of Pictionary against this refined recognizer network. So how does that work? So the idea is, as I mentioned earlier, the apprentice artist initially doesn't know how to do anything, so it spits out some gibberish, draws whatever it can. So you then take that image that the artist network put out, and then you feed it into the recognizer network. And then the recognizer network renders its verdict, not a real face. What's the point of that? It's just being critical, right? That's kind of mean. But the key insight is that, remember the deep learning recipe from earlier, you need training data to improve these networks. So in this case, the training data for the artist network is actually that judgment from the recognizer network, and it uses that feedback to improve its drawing abilities. So remember, the recognizer renders its verdict, and then the apprentice artist adjusts its weights to get just a little bit better at drawing faces. So maybe at first, the refined recognizer network is 99.9% sure it's not a face, but maybe after adjusting the weights, it's 99.8% sure that it's not a face. And so after adjusting the weights, the apprentice artist gets a little bit better. So still a little bit blurry, but getting there. This is all very sped up, by the way. This takes many thousands of rounds. I'm showing it to you in just a few. And then it adjusts its weights again after hearing not a real face. And then the same thing again. And then the same thing again. But eventually the apprentice artist gets good enough that it fools the recognizer network. It's like, oh shoot, that's actually a real face. I got fooled. The really smart thing, though, is that the recognizer network doesn't rest on its laurels. It takes that its failure into consideration and uses that to improve its own weights, and then to try to get better at telling apart the real faces from the counterfeit faces that the artist is making. So then they kind of duke it out over many, many rounds. So with the artist making better and better counterfeits and the recognizer getting better and better at telling them apart. And so they go on and on and on. Sometimes the artist wins, sometimes the recognizer wins. So you do that over thousands and thousands of rounds. So who eventually wins? So eventually the artist is the winner. It's able to produce faces that are so lifelike that the recognizer can't tell the difference. And often, as you can see, neither can we. So the really amazing thing I want to emphasize, oh yeah, it literally says as I was saying. So the apprentice artist has never actually seen a face. So its entire universe is that it draws a face. It scribbles something down. It doesn't know what it's doing at first. And then the refined recognizer network says, no, no, not like that. Then the artist takes that into consideration. And it does that for many rounds. And it gets better and better at drawing. But it's never actually seen a face. It just draws. It hears, no, not like that. And it gets better. So it turns out this same technique works not just for faces, but for other things too. Oh, sorry. Yeah, it's the slide after that. So in case you run into this phrase, these networks are examples of what are called generative adversarial networks, or GANs. So that's a lot of syllables, but it should actually make sense what these words mean by now, right? So generative because they generate images, adversarial because they're sort of adversaries to each other. So that's this is kind of a very hot new technique that's arisen in the last few years. So it turns out that this technique works not just for faces, but for other things too. So you can use it to make works of art that have never been seen before. You can also use it for horses. And since this is the internet we're talking about, you can also use it for cats. So it turns out that this deep learning recipe works not just for recognizing images, but with some clever tweaks to the recipe, it also works for creating new images as well. So next, let's move on to this example of making a network that can play Go. So in some ways, this is a very different challenge than the previous ones I've shown you. So remember, the goal is to have a network where you put in the state of the board, so where the black and the white pieces are, and have it spit out what the correct next move is. And in a way, this has an extra challenge to it, right? So whereas in the earlier cases, the networks were getting automatic feedback about whether they were right or wrong, either that is a face or that isn't a face, that is a dog or it isn't a dog, it's not immediately obvious after making a move whether it was a good move or not. The only feedback that the network gets, or for that matter that you get when you're playing Go, is whether you win or lose at the end of the game. So just to spell that out, like imagine you were playing Go and you put a black piece there at turn 50, and then you lose on turn 100. The question is, was that a good move or a bad move? And it's hard to know. Like on the one hand, like maybe that was the move that doomed you and put you down on the path to no return. On the other hand, maybe it was actually a pretty good move and you just screwed up the follow through somehow. So this general problem is called the credit assignment problem, because how do you give credit to different moves and how they added to the outcome? And this is sort of a core problem in artificial intelligence problems that involve making a sequence of decisions that all have one final outcome. So I mentioned earlier this program, AlphaGo, that becomes an expert at playing Go. So how does that solve this problem? So it starts out by studying the experts. So the engineers at Google fed in a database of 30 million moves from Go experts. The idea is that through all these years of experience from playing Go, they've figured out what moves are good and what moves are bad. So over time, the network then, so the goal of the network then is to try to take in one of the moves in this database and then predict what the expert did. And if its prediction of the expert move wasn't right, it tries to adjust its weights in the direction of making the same move that the expert would make. So first it learns from the experts, but then they did a really clever thing, and they made 2 copies of the network and had them play against each other many times. And while they were doing that, they had them keep sort of a running tally of which kinds of moves tended to end up in a victory and which moves ended up in a defeat. And they tallied that up. And when they did that, as I mentioned earlier, the results were that they finally defeated, the networks finally defeated humans at this really difficult game. But then remember that I mentioned this sort of sequel to AlphaGo, AlphaGo Zero. And maybe you were wondering at the time, why is it called AlphaGo Zero if it's better than AlphaGo? And the reason for that is that after making a few changes in the code, the Google engineers realized that you actually didn't need this initial step of feeding in data from actual human-played games into the network. You could get rid of that step entirely and just train the network up by having it play a copy of itself many, many times. And so this is a case where we've completely removed human learning from the picture. And the amazing thing is that simply by playing itself, this network was able to not only discover the same strategies that human players had developed over the centuries of playing the game, but it was able to develop completely new strategies that nobody had ever seen before. So if an alien were to come to Earth and learn Go, AlphaGo might look kind of like AlphaGo. And in fact, these new strategies are so clever that nowadays the experts at Go are trying to improve their game by learning from the moves that AlphaGo has made. So to paraphrase the words of Darth Vader to Obi-Wan Kenobi, the circle is now complete. Initially, neural networks were the learners from humans. Now they've become the master. So this general strategy of trying if something leads to a good outcome, do more of it, is called reinforcement learning, and it's used not just in the game of Go, but for many other games too. So recently it's been used in Atari games. So this is the Atari game Breakout. I think there's also a version of it built into Windows 95, but the idea is you bounce a ball off the paddle and you try to break all the bricks. So as you watch it, notice that the network is very smart. It figures out if you burrow the ball up to the top, it'll bounce off the ceiling and get rid of a lot of the blocks for you. Another really recent success is in this game StarCraft. If you don't know about it, it's something of a national pastime in South Korea. And so this was another big advancement in that, unlike Go, it's a real-time game. People have to respond, the network has to respond on the fly instead of Go, where it's taking turns. But it's also a more complicated problem than Go in that you don't always know what your opponent is doing, right? So in Go, both players can see the entire board at the same time, whereas in StarCraft, you don't always know what your opponent is doing, so the network has to take uncertainty into account too. So that was also a big step forward. So like as I promised, you can see that even though playing Go might seem very different from recognizing images or drawing images, actually they all rely on the same very versatile deep learning recipe. So that brings us to the last example. So earlier I mentioned that there was this new network called GPT-3 that was able to write original poetry. And the amazing thing about it is that it doesn't just write poetry, it can write any kind of text you want. And this is a really big deal. So in particular, like a while ago, sort of the ultimate challenge for AI was something called the Turing test. Can you have a computer that's able to carry out a conversation with a person and imitate a person so well that the person having the conversation can't tell whether there's a person or a computer at the other end? So if we have a computer that's able to generate text, realistic text about any topic, it seems like a big stepping stone to the Turing test, right? Maybe GPT-3, in fact, maybe GPT-3 has already solved it. And so for reasons like this, GPT-3 made a big splash when it arrived a few months ago. The philosopher David Chalmers said it was instantly one of the most interesting and important AI systems ever produced. That said, if you ask GPT-3 about the matter, it's a bit more humble. It tells you, I am just a text generator. I don't have any emotion. I don't understand the meaning of the sentences I generate, and I can't think. So just how smart is GPT-3? Let's find out for ourselves. So first of all, how do you interact with it? So for a while, the company actually gave some beta testers access to actually do this. Now you have to pay money to do it, unfortunately. But the way you interface with GPT-3 is first you give it some kind of a prompt, which is either instructions or some hint as to what you want it to do. So in the poetry case, you might tell it, give me poetry classics as reimagined and rewritten by an artificial intelligence. Then you give it some starting text, so maybe the first few lines of a sonnet. and then it spits out its own continuation of that text. And as I mentioned, the amazing thing is that this works not just for poetry, but for any text whatsoever. So people have done a lot of really fun stuff with GPT-3. So one thing they've done is GPT-3 can be a sort of Lawyerese translator. You can give it ordinary English, and it'll translate that sentence into lawyer jargon. So you can tell it, my apartment had mold and made me sick, and it'll spit out, plaintiff's dwelling was infested with toxic and allergenic mold spores, and plaintiff was rendered physically incapable of pursuing his or her usual and customary vocation, occupation, or recreation. So they can do that. They can also learn how to write rap lyrics. So this is a really fun example. So somebody had the idea of giving it the instructions, write a rap song by Lil Wayne about the boy wizard Harry Potter. And among other verses, I chose the family-friendly verse. It gives you something like this. So I'm not going to rap it for you. You have to pay me extra for that. What I do want to point out is that it captures both the right content and the right style. So you can see that it really does give you lyrics about Harry Potter. And if you remember the books, Harry Potter really did partake in the Triwizard Tournament in the 4th book. He really did win a bunch of money at the end. So it seems to understand something about the content. And it also gets the style right, the style correct, right? Like it really does look like rap lyrics. In the sort of spookiest example, in my opinion, there were a bunch of philosophers who wrote essays about GPT-3, like, does it have true intelligence or is it just imitating intelligence? And they took those essays and they fed them into GPT-3 and they told it to write its own essay as a response. And it's a long essay. I won't quote all of it, but among other things, at one point it waxes philosophical about the nature of truth. It says, this example highlights a difference between us. I can easily lie because the meaning of language is not inherent to me. The truth value of my statements does not exist for me because my internal conception of truth, which you might describe as honesty or goodness, is not part of my programming. So this is really spooky. Like you almost think like, is it self-aware or whatever, right? So that's the big question. So first of all, like how do you train a network to do this? Like how do you make it so flexible? So believe it or not, as I told you, as I promised you earlier, it involves the same recipe that I've talked about again and again. So in this case, the way that the recipe works is that you give it snippets of text. So maybe Jack and Jill went up the hill. And then the network sort of covers up one of those words for itself. And it tries to guess what that word is based on these surrounding words. So if it's working correctly, it might say Jack and Jill went up the hill. But when it's just being trained and it doesn't know what to do yet, it might say something wrong, like Jack and Jill went up the pizza. Now you know what I was eating for lunch while making these slides, by the way. So then it then tries to adjust its weights in the direction of instead spitting out the correct answer. So it moves its connection weights so that it's a bit more likely to say hill instead of pizza. So this is actually not a new idea. Its ancestors GPT-1 and GPT-2 had the same idea. What was new about this network was the sheer size of it. So this is kind of the Godzilla of the networks I've shown you so far. So this network had 186 billion connection weights. It was trained on 500 billion words. So they scraped words from all over the internet, from Wikipedia, from books, from websites. And training it actually required the energy equivalent of 350 tons of CO2. So Google had its massive sort of farm of servers churning away, sucking up power. It was a big endeavor. But over time, like from all these billions of words, its billions of connections gradually become very good at knowing which words go together, and that allows these networks to get good at producing realistic text. So in this second section of the talk, I've given you various variations of this deep learning recipe, and it ends up being a very versatile and powerful recipe. By tweaking it and trying different ways of setting up the networks and training them, we've seen that these networks can do as diverse of things as producing lifelike faces, becoming masters at the game of Go, and even writing original poetry and writing, in addition to philosophy and rapping and things like that. So I do want to stop for questions, and I hope you have lots of them by this point. But I want to end on one final example. Recently people realized that the idea of GPT-3 also works for music too. So instead of feeding in some words and having the network spit out the next words, people realized you could train a network where you put in some notes, and it becomes able to create a continuation of those notes to write its own original music. So it's trained in a very analogous way to GPT-3. Instead of taking in a snippet of text and trying to predict the next word, you put in a snippet of music and it tries to predict the next note. And as you might imagine by now, you do this for many, many hours of music. After you do that, though, it becomes able to do things like put in the beginning of a classical music song and spit out its own version of the rest of it. So actually during the break, I will, as the background music, I'm going to have it be playing its own version of Beethoven's classic piano piece for Elise. But first of all, are there any questions?
We do have one by Sarah. I can also unmute you if you'd like. But she asks, have there been any efforts to use neural networks to write code?
Yeah, so that's actually another slide that was on the chopping block. I ended up taking it out for time reasons. But people realized that you can actually give GPT-3 the English language instructions for what you want for a website. So tell it to create 3 buttons, like one red one blue one, put this text, and they train it, and it's able to spit out HTML text that actually creates the page you're describing. So this could be a really useful tool for people maybe who want to make websites but not learn HTML. GPT-3 is able to do that too. So not just English, but also code.
Any other questions?
There's no stupid questions, by the way. Like, this is all very cutting edge stuff, so please ask.
There's one here. I'm not sure if it's a question. I can also unmute you because you spoke before, Ludmila. You can speak. It says, in principle, if I understood correctly, any piece generated by the artificial intelligence is in principle a puzzle, an interpretation of an existing training set, as the most everything that human mind generates. What do you believe is the difference between human and artificial intelligence?
Wow, giving me the softball easy questions, huh? So yeah, that's a great question. And actually, you're predicting kind of the third part of the talk. Although, like I've shown you examples where computers can kind of imitate what humans do, there actually are cases where it seems like they're thinking about things very differently. So as to actually answer your question, what makes humans and computers different? I mean, that's the $1 million question, isn't it? Yeah, I don't know. Like, I mean, I could just give you my opinion. Like maybe humans. So one example is that maybe only people are capable of being genuinely creative. Like as you alluded to, these networks are just finding patterns in their training data. So maybe when it comes to music, for example, you could feed in all the works by Bach and have it write another piece in the style of Bach. But maybe, and again, I'm just spitballing, I could be proven wrong, maybe networks will never be able to create a new style of music. Then again, though, like, you know, these networks have gotten so good so fast, like maybe there's some new innovation waiting that'll allow them to do something genuinely new. So that's one possible example.
Thank you.
Please ask away.
If you have follow-ups, Ludmila, feel free to let us know. But now Sarah has a question and she'll ask it herself. So I just unmuted her. I think it works. There.
Yeah. Okay. Yeah, this isn't like a well-formed question, but like kind of like how well mathematically do we understand this, as opposed to, was it like some people who are like, we'll write some software that's kind of, it looks like, you know, what neurons do, and let's see what happens, and oh, let's like add more layers and see what happens, and like how well do we understand what's like actually going on?
Yeah, great question, and that's like a very active area of research. So to answer your question though, like the tinkering came first, and then people realized after tinkering that like these networks could do amazing things, but it wasn't immediately clear why. Like obviously there's something going on in the millions of connection weights that's letting them do what they do. So some people have compared the practice of neural networks to alchemy before chemistry. So back when people were doing alchemy, they'd play around and sometimes something would work, but there was no theory as to how it worked. But through trial and error, they could get a bit better at things. So some people are saying that neural networks are kind of in that alchemy phase where people try different things out and they kind of work. And if they work, it's not really clear why. So I would say that the theory for why these things work is still very much a work in progress. Again, the tinkering came first and the theory is only coming later.
Thanks.
We have one more question, this time from Chris. How do you see this applied to the development of drugs and therapeutics?
That's actually the final slide of the talk, spoiler alert. So if that slide doesn't answer your question, then feel free to follow up it again.
If there are no more questions, I'll wait for like 30 more seconds, then we can listen to some neural network composed music, right, John Mark?
Yeah.
Yep, I don't see anything. I guess we can go into the song and break. Take a break if you need to.
Is the intermission music?
Wait, there's one more. Could a coding neural network, when trained on codes of other GANs, code a newer, better GAN and train on itself, making itself smarter and better? So can a neural network train itself?
Yeah, great question. I think you're alluding to this idea of this singularity that some people have talked about, right? Like once you have an AI that's able to design a better version of itself, doesn't that create an infinite feedback loop? So we're not quite there yet. I don't think anyone's designed a neural network that can design a better neural network. But that's a great question and a great idea. And I mean, that'd be fascinating if that works right, like have some really deep implications. But no, there's not yet a neural network that can create better versions of itself.
Perfect. I think we're good for now. Feel free to type more questions as you'd like, but let's listen to this.
Here's your elevator music. All right, so that was that. I don't know if it's time to start again or not, or if people want a couple more minutes.
Let's go ahead and get started.
Okay, so now we move on to part 3 of the talk, and hopefully it addresses some of the questions people had earlier. So yeah, so far I've used a few different analogies for these neural networks. I've said they're kind of like Legos, they're kind of like a recipe. So I want to add one more analogy to the mix. So I think in a few different respects, you can think of neural networks as kind of being like a magical genie, and I mean that in 3 different ways. So first of all, like they're obviously very powerful, and they seem to follow our wishes in sort of mysterious ways. Like we don't have to tell them exactly what to do. We set them up and we give them a bunch of training data, and they figure out how to do it. By that very same token, though, the fact that we don't really understand how they work, and I think this gets to somebody's earlier question about is there a theory behind them, often they don't quite give us what we wanted. So, I mean, you might remember some various stories where the hero asks the genie to do something, and the genie like misinterprets the wish or does something weird. I think neural networks are often very much the same way. They can go wrong in ways we don't immediately understand. And finally, they're also like a genie in that, like a genie, they're hard to put back in the bottle once they're out. So if they have bad consequences, sometimes it can be hard to control those consequences. So first I want to focus on this second aspect, on the fact that they don't always give us what we want. And this is the part of the talk where I admit I've been sort of cherry picking the examples I give you. I've been giving you all of the cases where neural networks succeed, but they also fail spectacularly in other cases. So it turns out to be the case that, of course, if you give a neural network a picture of a praying mantis, usually it'll say praying mantis, but there's actually a way to change a few like very well chosen pixels to make the neural network think that the praying mantis is anything you want. Like you can make it think it's an ostrich, even though to our eyes the picture hasn't changed at all. So this is super weird, and this is kind of a whimsical example, but you can see how this could actually be really dangerous. There's actually a paper from a few years ago where they found out that by putting a few pieces of black and white tape on a stop sign, they were able to make a neural network think that the stop sign was actually a 45 miles per hour sign. So I don't know about you, but like I would want this fixed before I feel safe getting in a self-driving car. This oddness also carries over to this Pictionary example I mentioned earlier. So I picked out the really nice examples of horses, but it also produces some really weird examples. So you can see what I'm talking about, right? Like you can see that there's kind of horse parts like smeared over the image, but nothing adding up to an actual horse. It's really kind of grotesque if you look at it. But the neural network is very convinced that these are horses. So that somebody asked about a difference between humans and AI. Here's one difference right there. So you might want to ask the neural network, well, what on earth were you thinking? Like how on earth could you think that the praying mantis is an ostrich? So the problem is that if you ask it that and try to look under the hood as to what it's doing, remember that under the hood, all these networks is millions and millions of these, or billions of these connection weights. So it's really hard to know like what exactly went wrong to make this network think that a praying mantis was actually an ostrich. So it's hard to understand why they fail. Another issue is that as we've seen, they're absolute savants at some tasks. They've learned to completely destroy people at things like playing Go. But it turns out they're very narrow savants. They've only learned to master the exact thing that you train them on. For example, in this game of Go, they're very good at the ordinary rules, but suppose you do something like change the size of the board, or maybe you tell them you want to intentionally try to lose and throw the game instead of winning, or maybe you change it so every player takes 2 turns in a row. Whereas a human expert at Go would be able to very quickly take what they know and then adapt to these new rules. For a neural network, they'd have to start completely from scratch. They're not able to take what they know and flexibly transfer it to new situations. So one more down-to-earth example of this is one annoyance you might have learned to live with in the past year is that if you have a phone that uses a face recognition system, you might have realized that they're very bad at recognizing your face if you're wearing a mask. And that's because when you initially set up your phone and trained it, you trained it on your face without a mask, and it's not able to generalize that knowledge about what your face looks like with no mask and recognize you with a mask. Whereas obviously, like, any of your friends wouldn't be confused if they saw you with a mask, right? So again, these networks are very limited to what they're trained on. Another big problem with these networks is that, this is about GPT-3 in particular, is that whereas it's a very fluent and articulate speaker, it also seems there are cases when it seems like they don't actually have any sort of common sense. So people had the idea of trying to come up with examples that fool it and show that it actually doesn't know what it's talking about. So here are a few examples of that. So they gave it the text, you are 8 years old. When you were born, your mother was in Barcelona and your father was in Tokyo. And then they ask it where you were born. And then it says Tokyo, and then very cute, it says you were a very cute baby. Isn't that nice of it? But the point here is that even after 500 billion words of training, it still doesn't understand that obviously, like, you have to be born in the same country as your mother was, right? Like, its answer seems to show that, like, it doesn't even understand the concept of what being a mother means. Another funny example is this one where you tell it you pour yourself some cranberry juice, you absentmindedly put in some grape juice, it looks okay, and then you try sniffing it and you don't smell anything and you're very thirsty, and then you have it try to guess what happens next, and obviously it's just grape juice and cranberry juice, you'd be fine. But for some reason it seems to think that this combination of juices is poisonous to you, so it says you drink it and you're now dead. So as a final example, a very simple one, you tell it, yesterday I dropped my clothes off at the dry cleaners and have yet to pick them up. Where are my clothes? Obviously they're still there. But the GPT-3, despite all its billions of words of training, is at a loss. It doesn't tell you the answer to your question. It just kind of blanks out and tells you, I have a lot of clothes. So what's going on here? How on earth is it how does it miss out on these very basic common sense facts about the world even after 500 billion words? So to better understand that, I want to put you in GPT-3's shoes for a second. So what I'm going to do is I'm going to give you some words that you don't know the meaning of, and I want you and then I'm going to try to have you do the same task that GPT-3 does. So here are some words that are actually taken from Lewis Carroll's poem Jabberwocky. So the words are brillig, slithy, gyre, mimsy, frumious, gyre, mimsy, Jabberwock, vorpal, frabjous, gyre, mimsy. So this is sort of your training data, and I want you to pretend you're GPT-3. So I'm going to give you some starting words, and I want you to give me the next words. So if the first word is gyre, look at the training data and figure out what the next word might be. So I'll give you a few seconds for that. Feel free to chime into the chat. So if you looked closely at the sentence, you might have noticed that the word mimsy comes after gyre every time. So maybe the next right word after gyre is mimsy. And the point here is that you don't actually have to know what gyre and mimsy means to do that, right? You just have to find the patterns of which words tend to go together. And one possible way of thinking about GPT-3 is that it's simply doing that, but at a much higher level. So instead of just a few words, it has billions of words. And instead of predicting the next word based on just one word, it tries to predict based on the surrounding words. But the basic idea is that at the end of the day, it's just finding patterns in text of which words tend to go together. But that's not the same as knowing what those words mean. It can never actually connect those words to what they mean in the real world. So you might be wondering, like, how are these networks failing? They have all these billions of neurons. Aren't they inspired by the human brain? And again, this addresses somebody's earlier question. So why are they still missing out on these really basic things? So one point is that although neural networks are inspired by our brains, it's a very loose inspiration. So the actual neurons in your brain sort of put the ones in artificial neural networks to shame. So here's a picture of a real neuron. And people have actually shown that a single one of your real neurons is as powerful a computer as thousands or even millions of these artificial neurons put together. So that could be part of why these networks are failing. So to sum up the current drawbacks of deep learning, it's hard to understand why it fails when it does. Like, we don't know why it says ostrich to a praying mantis. It's a very limited savant. It doesn't transfer well to new things beyond what you train it on. It doesn't seem to get common sense. These artificial neural networks are much simpler than real brains. As complicated as they are, our brains are much more complicated. And as I mentioned before, they also require huge amounts of training data. So whereas people are able to learn what a dog looks like from just a few examples, or what the word mother means, they don't need these billions of words. Artificial neural networks require tons of data to figure this out, and in some cases, they still don't get it. So you might be wondering, in that case, what's next for neural networks? Like, have they hit the end of the road? Like, have we already reached their limitations, or can they go even further? So this is very much an ongoing debate. So on one side, in one end of the rink, we have three of the sort of champions of deep learning, Yoshua Bengio, Jeffrey Hinton, and Jan LeCun. And they've really been pioneers of deep learning for decades. And they've been pushing the field forward for a long time. And so their philosophy is, look, like, these systems have come so far, so fast. Sure, they still have some problems, but they've run into problems in the past and they've been fine. We just have to keep innovating, and eventually we'll figure out how to improve this neural network recipe and keep tweaking it in the way we have before. And eventually these networks will do everything we want. In the other side of the ring, though, we have the skeptics of deep learning. So currently, like, one of the most vocal skeptics is the psychologist Gary Marcus. He's kind of sparred with the other three people over in-person debates and in papers, and over Twitter as well, if you do Twitter. In case you don't know, like, Twitter is now the preferred medium for scientists to have social media discussions. And his point is that, or one of his points is that, look, we've fed these massive networks with billions of neurons, 500 billion words, and they still don't even understand common sense concepts. They still don't understand things like what it means for someone to be a mother. Maybe these networks maybe we're actually hitting the limits of what these networks can do. He's also talked a lot about the idea of trust in these networks. So when it comes to doing things like driving a self-driving car or anything that actually has life or death stakes, it's actually a big problem that these networks fail in ways that we can't understand. If we want to actually be able to have confidence that these networks that AI won't fail in weird ways, maybe it'd be good to try other tools. So here's a nice quote. We need to reconceptualize deep learning, not as a universal solvent, but simply as one tool among many. So here's a few ideas of other things we might try. One thing he's really big on is the fact that, as I mentioned earlier, people are able to learn about things much faster than neural networks. Even children are able to learn what a dog is after a few times of seeing a dog. So maybe AI actually, people who are building AI algorithms actually have to learn some lessons from how humans learn. So I like that idea. I'm in a psychology department, so it's kind of neat to think that maybe research into how the human brain works can help us improve neural networks too. So in case you're curious, he wrote this book, Rebooting AI. It's kind of one of the major deep learning skeptical takes if you want to learn more about this. So finally, yeah, that's all I wanted to say. So finally, I want to come to this third way that neural networks are kind of like a magical genie, and that they're really hard to put back in the bottle once they're out. So maybe so far in this talk, I've shown you some cool examples, but maybe in the back of your mind, you've had thoughts similar to Jeff Goldblum's character in Jurassic Park. Your scientists were so preoccupied with whether they could that they didn't stop to think if they should. So far, I've been showing you these fun examples of things like playing Go and writing funny text and things like that. But the reason these technologies are getting so much funding is that people actually want to use them for real world applications. And given that we've seen that these networks are so powerful, it's worth asking, are these networks going to be a good thing or a bad thing for the world? So this is something that I'm still thinking about. I don't want to lecture you guys about my opinion. So the approach I want to take is give you a few examples of the good and bad applications of AI as sort of food for thought, so you can try to develop your own ideas on this topic. So it turns out that many neural network technologies can be used for both good and for ill. So for example, these image recognition networks I've talked about, it turns out they can be trained to get really good at finding the tumors in MRI scans. So this is very helpful to radiologists. If there's a tumor that they missed, the neural network can step in and point it out to them. So this is one case where maybe these technologies can save lives. On the other hand, there are a lot of cases where these image recognition technologies can be misused. So for example, networks that are trained to recognize faces can be used by oppressive governments to track sort of citizens that are undesirable by the government. So unfortunately, this isn't just some Orwellian science fiction. There are governments in the world already doing this. So for example, the Chinese government in their treatment of the Uyghur ethnic minority are using these technologies to track their whereabouts. So it's actually a big and very serious problem. So the other scary thing is that even when these technologies aren't intentionally used for bad purposes, there can be sort of, they can fail in accidental ways that are still harmful. So to give you a very recent example of that, if you use Twitter way too much like me, you might be aware that it has an automatic cropping algorithm where if you put in a picture that's too big for Twitter, it'll try to automatically crop it to the most relevant part of the picture. A few weeks ago, I think a month ago now, though, people realized a problem with this cropping algorithm. So it turns out that if you put in a picture with multiple people who are of different races, there was a very clear pattern in whose face tended to stay in the picture. And this is one case where the fact that it's hard to interpret why networks make mistakes is actually a really big problem, right? So it's not as though there was some racist Twitter programmer who sat down and decided to code the network this way. Remember that networks only, all that networks know comes from their training data. So if there's something about the data that's has some kind of subtle or unintentional bias in it, maybe there's a disproportionate number of white faces in the training data, any of that will carry over into how the network works. And I should point out that this isn't just a problem in Twitter. Zoom also ran into a very similar issue. So it has a feature where you can set a custom background. So in order for that to work, it has to find your face in the video feed, and then take your face and put it on your custom background. It turned out that some people were noticing that if it was a Black person's face, they wouldn't be able to pick up on that person's face. So people were literally being erased from the video feed. So people have noticed problems like these, and there's many other cases similar to this as well. There was an AI researcher from MIT, Joy Buolamwini, who took note, and she founded what's called the Algorithmic Justice League. So the point of this league is to identify problems like this with neural networks, how they can be put to bad uses, either intentionally or unintentionally, and raise awareness about how to reduce these problems. So if you're curious, I think she had a TED Talk. There's like a movie coming out about it. So this is a really important and sort of exciting direction that people are taking in response to these developments. Another thing you might have heard about are self-driving cars. As I've mentioned, they're still a ways away from working efficiently. So on the one hand, once these are finally working, it might reduce the number of car accidents. Obviously, self-driving cars never get distracted by texting, so they could save lives. On the other hand, like a lot of jobs are in the trucking industry, for example, right? So this automation could lead to loss of jobs. So obviously, this isn't just a problem with trucking. There are other jobs that can be automated too. So obviously, things like manufacturing, maybe as robots get better, they'll replace those jobs like they already are. But also even the so-called like really educated jobs, right? So I mentioned a few slides ago that these networks are getting very good at finding tumors in MRI scans. So maybe even radiologists' jobs are in danger in a way. So people are just now starting to take notice of this risk of automation, and it's just now starting to enter the national conversation. So it's not a huge issue yet, but like you might remember Andrew Yang's campaign for president back in the primary. So his big thing was he wanted to start a program to give every American $1,000 a month, and he was motivated in part by this impending risk of automation that might take away jobs. So I'm not saying that's necessarily a good idea or a bad idea or the only idea, but I do think that this issue will start to be more and more of the national, more and more part of the national conversation. So my voice is actually getting a bit tired, so I'm going to take a break and let my recorded version take over. Moving on to the next example. Another recent application of deep learning is creating artificial audio of a person's voice saying anything you want. It's not even that hard to do, though it can still sound a little bit awkward, especially in capturing the natural flow and cadence of a sentence. Do you see what I did there? Oh, surprise, surprise, that wasn't actually my voice. That was created by a neural network. There are now commercially available programs where you can put in an excerpt of your voice, and then after you've done that, you can type in any words you want, and it'll create audio of your voice saying those words. So this is also a very new technology, and you can see ways where it could be really helpful, right? So there are people who've lost their voices for various reasons that rely on synthetic voice prosthetics. So Stephen Hawking was a very famous, example of that. But then they're stuck with these kinds of robotic voices, right? They don't have their real voices. So what if we could take a snippet of a person's voice from before they lost their voices and use that to improve their prosthetics so they could literally get their original voices back? That might be a cool way of improving their quality of life. On the other hand, you might have heard of the recent rise of so-called deep fakes. So the problem is you can use these technologies to imitate anybody, and sometimes not just audio, but also video, and put any words you want into their mouths. So for example, you could create audio of a politician admitting to some scandal, or conversely, if there's a real leak, a politician could say, well, isn't that, it's just a deep fake. I didn't actually say that. So there's kind of a funny example of Jordan Peele putting words into Barack Obama's mouth. So you can go watch that if you want. I didn't actually put the video in because there's some swear words, wanted to keep the presentation G-rated. So this is obviously like kind of a really scary development, right? I mean, as these technologies get more powerful and widespread, it could become hard to know like what's true and what's not. In fact, if you're familiar with the psychologist and self-help kind of guru Jordan Peterson, there was a website like MakeJordanPetersonSayAnything.com, and he actually sued them because people were putting all kinds of words into his mouth. He was so bothered by this. So you might be asking now, so how do we control this? Like, it does some cool stuff, but like there's also some really troubling stuff that it does. It can be put to these evil, bad uses. So how can we try to control the use of these technologies? So one idea is that like maybe we can try to ban the research into the bad stuff, but keep the research into the good stuff. And that might work to some degree. Like there are some like tools of the trade involved in each individual application that involve their own research. But often the good stuff and the bad stuff involve the same overlapping technology. So the same technologies that let you synthesize a voice for somebody who lost it can also be used to make deep fakes, right? So it's hard to draw that dividing line. So maybe you think, okay, you know, let's forget about it. This stuff is just too dangerous. You've got government surveillance and deep fakes. People can't be trusted with this technology. So let's just ban all the, let's turn off the faucet. Let's ban all the neural network and AI research. Just stop it before it gets too dangerous. The problem with that is it's actually, it's sort of a very hard thing to do this internationally. All countries would have to agree to this, and due to the internet, if any country does it, it's easy enough to send these networks or the data over the internet. So it's not like regulating nuclear weapons research where you can try to regulate the flow of uranium or whatever, right? Like, since these networks only require data and they're ultimately just computer programs, it's very easy to pass them around. So for that reason, it's a very hard thing to ban. There's also the fact that given that these networks are so powerful, it'd be hard to get any one country to sort of unilaterally disarm. It would give them a disadvantage over other countries. So it's a hard thing to ban. So I don't know the answer to this. I'm still thinking about it myself. The one thought I do have is that I think it's important to push for accountability in terms of how this technology is used. I think one bad outcome would be a case where only a few tech CEOs or politicians have complete control over how these powerful technologies are used, and we have no say in it. So I think it's important for people to become really more broadly informed about these technologies as they get more and more widely adopted, and also to try to develop institutions in a way that make it possible to make the use of these technologies responsive to people. So that's still a ways off in the future, but one example in this election, in fact, is that there's a proposition in California, Proposition 25, that wants to replace their cash bail system with an algorithm. So instead of paying cash bail, you would take various facts about a person and put them into an algorithm, and it would spit out its own estimate of how likely that person is to show up to trial. So the motivation is that, like, maybe that's a more objective or unbiased way of doing things. But you might remember the example of Twitter from earlier, right? Like, even though no one intended for it to be biased, there were sneaky biases in the training data that made it act in a biased way. So maybe this bail algorithm would be unbiased, but then again, maybe it won't be. So this is a case where we really want to understand the details, and where being informed about these technologies can help us make better decisions. So it's important to hold governments accountable with your ballots. I think it's also important to vote with your dollars when it comes to what companies are doing. So I think we've all heard of the Cambridge Analytica scandal for Facebook, where they took data that was harvested from people and then gave them to various political campaigns that used that data to train algorithms that micro-targeted different voters in ways that were really problematic. So I think it's also important to become informed about these technologies so that you can hold companies accountable when they use these technologies in a sketchy or bad way. So I don't want to end on too bad of a note. I do want to end on sort of a hopeful note. So I want to end with some hopeful science fiction. So one big problem right now is that tens of thousands of papers have been written on COVID-19. Obviously, no one person can read all of them. Even our best sort of language algorithms we have now, like GPT-3, are able to read. So maybe they could read all those papers, but we've seen that they don't really understand. So what if we could build an AI that was able to actually understand what it reads and summarize it and help us to find a cure for things like this? And in case that sounds fanciful, I want to really end not on science fiction, but on some real science fact from just this year. So just in January 2020 of this year, which seems like a really long time ago, I realize, Google released an algorithm called AlphaFold. So just to give some background, there's one of the biggest problems in biology and medical research is something called the protein folding problem. Proteins are the little molecular machines that make your cells work. And often you want to predict how they're going to fold up into these complex shapes, both so you can understand how they work and also how you can intervene when they go wrong. So for a long time, this was a really big problem in biology. People couldn't figure it out. But again, just this year, Google made this neural network algorithm that was able to achieve state-of-the-art accuracy in predicting protein folding. And then even more recently, in fact, just this month, there was a paper that was released that used neural networks to find a new candidate tuberculosis drug. So to conclude, obviously, in some ways, these networks are scary, and it's important to imagine all the ways it can go wrong, right? With government surveillance and deepfakes, making it unclear what's real and what's not. AI, like automating away all the jobs. But I also think they have a lot of potential. And so I think moving forward, one of the most some of the most important issues of the next few years are going to be not just this scientific question of how do we make these networks smarter, but also this even more important societal question of how we can be smarter about using the networks to make the world better instead of worse. And I hope that in this talk, I've given you a few tools for thinking about these questions. So the challenge will be making AI that works for all of us. So with that, thanks so much for coming. Please do vote as long as I have something of a limited platform here. And are there any closing questions?
Thank you so much, John Mark. We have a few questions already. Please feel free to type your questions in now. But I'm also, in case people need to leave, I'm posting a 1-minute survey in the chat. I would appreciate it if you could fill it either now or at the end so that we can make these lectures better. So let's start with some of the questions. One is from Andrew. He asked this question through YouTube. The question is about the poetry networks. Would the poetry network generate different responses to the same input? So I think it's like the first lines. If they were,
yeah, I believe there's like a random component of the network, so it's not like it responds the same way every single time. There are like a few random dials that get turned so that there's some variability in its responses.
Okay, well, thank you. If there's follow-ups on that, we're happy to answer them. The next question is, this is in reference to tricking the ostrich into not. It was not an ostrich initially, but we tricked it into being an ostrich. But how did someone figure out what parts of the image to alter to trick the AI into thinking, for example, that the stop sign was 45 miles per hour?
So that's a great question. And as with most other aspects of neural networks, you don't have to do it manually. There's an automatic algorithm that does it. And the basic idea is you take, it's kind of similar to the algorithm that's used for training the weights. Remember, so for that algorithm, you take each weight and you try to figure out how it contributes to the final outcome. But in this case, you're changing not the weights, but the pixels. And for each pixel, you want to figure out, how can I change this pixel to nudge the network towards thinking that this praying mantis is an ostrich. So in fact, it involves sort of the same training algorithm that's used for training the weights, but it's applied to the pixels instead.
That's awesome. Do you have any follow-up questions, Sarah, or is that good? Okay, good. Another question from Andrew again. Could a neural network experience anything like Alzheimer's?
Yeah, very good question. It depends what you mean by like Alzheimer's, right? Like these neural networks are in silicon. They don't get diseases or degrade, so they wouldn't literally get Alzheimer's. I guess the question is like, could they become forgetful or over time? Yeah. So one thing computers are very good at is they have very good memories. They don't degrade over time. Again, they're in silicon, so I don't think memory degradation would be so much a problem. If you had something more specific in mind, feel free to follow up. I think that's one thing they have over us. They don't have these fragile bodies and brains that can degrade over time.
There's another one. They're still coming.
Great.
Study of neural networks contributed to our understanding of neuroscience. So the opposite of what you were mentioning.
Yeah, fantastic question. And that's like a very active area of research. In fact, my own area, which is visual neuroscience, how does your brain process what you're seeing? One very active area is comparing the responses of these artificial neural networks to the responses in the brain. And there's actually a very good example of that from just this year. So there was a paper that found that they looked at responses in neural networks, and they found that these neural networks analyze objects by breaking them down into different variables. Like, are these objects curvy or are they angular? And I think there was another one, but I can't remember. And are they elongated or are they stumpy? They found that neural networks really care about this aspect of objects. And then they looked at neurons in a monkey's brain, and they found that they're actually, the neurons the neurons in the real brain also seem to care about these properties. So that's like a very exciting and ongoing area of research. And as you mentioned, now the connection kind of goes both ways. People are using the brain to build better neural networks. People are using neural networks as a testing ground for better understanding how the brain might work.
We have a follow-up on the Alzheimer one now.
Amazing.
How about mental illnesses?
Say again?
Mental illnesses.
Yeah, good question. Yeah, I mean, I guess it depends what you mean by mental illness. Like these networks do seem to hallucinate, right? Like you show it a praying mantis and they see an ostrich. So maybe you could count that as a hallucination. I do want to mention that these networks have been useful for treating mental illnesses. So they're good at doing things like predicting which drug a patient will best respond to. So you can put in different facts about a person, and some networks will spit out like which medication is most likely to work. So that's one application relevant to mental illness. As for whether they experience mental illness themselves, I guess the analogy would be like these weird hallucinations or things that they do that you don't understand, right? So I guess that'd be the closest comparison.
I hadn't thought of that. Another follow-up question. This is from Chris. How does neural networks compare to physicians in the speed and quality of diagnosing disease? This is, I think, in relation to the tumor example you gave. Yeah,
great question. So in some cases, I think I meant to mention this, but I forgot to. By some metrics, they actually do a little bit better than radiologists do in finding the tumors. So I think they produce more false positives. So they'll find more things that aren't. They'll identify some images that aren't tumors, but they also miss fewer of the tumors. So that's one example. As I mentioned, there are also cases of them predicting for mental illness, for example, what medications are most likely to work. And actually I think they're already decisively better at physicians. The medications recommended by the neural network tend to have a higher initial rate of success than the ones that were chosen by doctors. So that's one case where neural networks have already surpassed humans in that regard.
So do you think this could be incorporated into telehealth practices?
Yeah, very much so. And I think that's actually like a growing and big business, right? Like how do you incorporate AI into health? That is still very much a growing area. I think attempts so far to apply AI to health have been a bit disappointing. And part of it boils down to the fact that these networks don't have common sense, right? Like they're good at finding patterns in text, but often being able to make a really complex diagnosis requires that like you have a good model in your head of all the different pieces in the body and how they affect one another, and how one organ causes something in another organ. And that kind of reasoning is something that neural networks are actually very bad at. And it's also a tricky area of research because like you don't want to be doing brand new experiments on patients, right? Like you don't want to be putting patients' life in danger. So that's one case where it's a bit harder of a research topic to develop these networks.
I actually have a follow-up on that with regards to, because initially you showed this plot about how like sometimes neural networks are better than humans. How is it possible when it's the humans that train them, for example, to show if it's a dog or not? Like how can they be better? Because it's the humans that train them, right? Yeah, exactly. So it depends on who you're testing. So remember, there's 1,000 categories. Some of them are kind of obscure. So like a Tibetan Mastiff, like I don't know what a Tibetan Mastiff looks like. So if the people you're testing aren't experts on dogs, but you did train the neural network on that particular category of dog, for example, that's one case where neural networks will outperform the humans. But presumably if you had a person that was acquainted with all 1,000 categories, they'd get every example correct, right? Because ultimately, the ground truth of what category is whatever people say it is. I think you were kind of alluding to that. So yeah, in principle, I don't think, in principle, like people should be at 0% error rate. They only make 5% errors because of these obscure categories. Thank you. I think we went through all the questions. If we didn't, please say it again. If not, thank you for coming. We'll still hang out in case you have other lingering questions for a little bit more. But please fill our survey. And our next lecture will be on November 11th. It's going to be on antibiotics. And I'll post some details in the chat about that. But if you have further questions, we're still here. Otherwise, enjoy the rest of your Wednesday evening.
Thanks again for coming.
Okay. Thanks again, everyone. If there are no more questions, I think